friends, today we are going to study about kinetic isotope effects, linear free energy relationship and hammett equation. What is kinetic isotope effect? The change of rate of reactions in a molecule substance by its heavy isotopes. By this, we can get transition state structure and its information of rate determining steps and the reaction mechanisms by determining the rate determining steps. So, kinetic isotope effect is a measure of ratio of the rates of reactions of two different isotopes. In the case of primary and secondary effects, it is the ratio of lighter isotope to the heavier isotopes. If we take the case of hydrogen and deuterium, we get kinetic isotope as Kh by Kd. So this is the kinetic isotope effect. If we the magnitude of kinetic isotope effect depends upon their positions, location of this as isotopic substitution. Where this isotopic substitution takes place, it determines. Now, what is it is classified as two. That is, first we are going to discuss about primary kinetic isotope effects. First, primary kinetic isotope effect. What is this? The change in the rate of reactions and the sites of bonding in the rate determining step. Now it arises due to the bond breaking completely or partially before or after the rate the transition state. So, origin of this effect, it depends upon the different frequencies of vibrational modes. That is, each vibrational mode has different frequencies, and we can calculate by using the equation nu is equal to 1 by 2 pi by root of k by mu, where mu it is the reduced mass. And each vibration mode has different levels, and this can be determined using another equation, that is n is equal to n plus 1 by 2 into h nu, where n can be 0, 1, 2. When n equal to 0, it is called 0 point energy. And if we take the case of a spring, it has a two ends. If it is one end, it is carbon and the other one is hydrogen. And in another case, if hydrogen, it is replaced by deuterium. In the CH bond, it has a bond length higher than the case of CD bond. When it gets stretched, they vibrate, and this stretch is more in the case of CH than that of CD. Why? Because CH, it is a hydrogen, it is a lighter isotope, while deuterium, it is a heavier isotope. So due to increase in the masses, their stretch decreases, because by increase in mass it will be difficult for them to stretch. So as K or force constant or M increases, there decreases in the stretch. Here the hydrogen has lighter mass than deuterium, so the stretch is more high in CH bond than that of CD bond, and due to this we see that 0 point potential energy is high in CH than that of CD. Now, if we consider the case of this graph, if we take this potential energy diagram, we see that CD, it is at lower than that of CH, and we see that from this we get ECH, it is less compared to that of ECD. Okay, and here we see that the differences is very large, and we know that in the primary kinetic isotopes, Kh by Kd, its maximum is equal to 7. Okay. Now, there is two types of prime mechanisms taking place. One is completely homolyzed, the other one is partially homolyzed. In that complete homolysis, the bond break completely before the transition state, and there is an absence of potential energy. Well, that is seen here. This is not present in the complete homolysis. This is a diagram for the complete homologous. The other one, it is partial. Second type mechanism is partial. Now next we are going to see that linear and non-linear in the transition stage. If we take the reaction AH plus B minus gives you transition state A minus BH, and in the case of non-linear we get so in these equations we get that the isotopic effect is maximum obtained for the hydrogen in transition state is at the straight line, while in the case of non-linear it is Kh by Kd, it decreases and it is about 1 to 2.6 range. And primary effect here, it has more stretching than that of bending. And now we are going to study about secondary kinetic isotope effect. In this secondary effect, here the substitution takes place and here the bond breaking does not take place during this course. And this Kh to Kd, it is less than 2. And we see that it is classified as alpha and beta, and this substitution is made made at the alpha or beta centers related to this reaction, bond breaking. So here this effect is determined by using a change in the hybridization. Here a change occurs during its hybridization, and in CH bond the decreasing order is of sp to sp3. Okay, if we take a reactions, that is we get another concerted reaction. In this both cases, here hybridization change takes place. From first case it is sp3 to sp2, second sp2 to sp3. Here CH intact and change in hybridization takes place, results in the kinetic isotopic effect. If here in the case of secondary, there mostly occurs bending than that of stretching. So we can explain by using in plane and out of plane. In plane, it can have like this. In this case, and the CH bond length, it is high. Here there is a steric effect taking place. If we replace it with deuterium also, there causes the same effect. While in the case of out of plane, there is a little steric effect compared to the in plane. and in the case of the second one, we see if a CH bond here also has a steric effect, while in the case of out of plane, in this case here no steric effect takes place because nothing is above or below the plane, so there is no steric effect, and here we see that value is also less, that is 800 centimeter inverse. Now if we take this is the potential energy diagrams of these two reactions. First one is sp3 to sp2. We see that here the CD is at lower because CD it has less destabilizing interaction compared to that of CH, and here that E2 greater than E1, and by this KH is greater than KD, and KH by KD greater than 1. While in the case of sp2 to sp3, there is a reverse scenario taking place, that is complete reversal takes place. Here we see that the reactant it is very less compared to that of transition state 0 point potential energy, that is here there is less small differences while compared to that of transition states, and here E1 is greater than E2, so KD greater than KH, so KH by KD less than 1. This type of reactions, it is inverse kinetic isotopes. This is known as inverse kinetic isotopes. Why here usually CH it moves faster than that of CD, while in this cases CD is moving more faster than CH, so it is inverse. So what is inverse kinetic isotope effect? It is a deuterium species moves faster than that of undeuterium species. It is known as inverse kinetic isotopic effect, and here it is deuterium moves more faster than hydrogen, and its value it is 0.8 to 0.9 the range. And now we are going to study next topic, that is linear free energy relationship, LFE in short, LFER, sorry, LFER. So what is this? Hammett found electronic properties in the organic acids and bases with their electronic equilibrium constants and its reactivity. The electron donating and releasing groups with their comparison with their benzoic acid derivatives and ionizations. So this LFER it is an attempt to quantitative relationship between the structure and the reactivity. If we consider the case of rate constants and equilibrium constants, it has a linear free energy relationship between that of the free energy. That is, if we take the equations for the rate constant, we know K is equal to K dash, that is Boltzmann constant, H by Kt by H into e raised to minus delta G by RT. While in the case of equilibrium constant, K is equal to e raised to minus delta 0 by RT. Okay, here both the cases there is a linear relationship between both the equations. Okay, now next the linear free energy relationship describes a polar impact on the reactivity in aromatic rings, and it is known as Hammett equation. In linear free energy relationship, we see that linear free energy relationships, if you take a reaction, that is two substrate reacts and forms an equation, that it goes through a series of reactions. In this series of reaction, there causes various changes in this equation. That is, if a reaction changes, then there causes a change in this reactions. If we take another one reactions and if it goes through this same way, in the similar changes taking place in the second reactions as the first one, they'll create a linear relationship between the first and second equations, and this is known as linear free energy relationship. And with this we can determine the illustrations of the reaction mechanisms. Now, next we are going to study Hammett equations. Hammett equation, Hammett equation is used to determine, it describes the reaction rate, rate constants and equilibrium constants with the benzene derivatives, with the para and meta substance, with the two parameters, that is sigma and delta. Hammett's relationship only applies to the systems where the substance are attached to the reaction center via aromatic rings with a meta and para substance. If it is an ortho substance, this reaction it will not be in the line. It will be out of the line due to the steric hindrance. And if it is an aliphatic acid also, it will not be on the straight line. It will be out of line. Now, in the 1937, Hammett recognized the electronic influence in the substrate X on the reaction center X, Y, and with the M and meta and para substrate benzene derivatives. And with this quantitatively this effect quantitatively this effect was obtained to hydrogen with a comparison with the delta G0 dissociation with the benzoic acid KX and with the benzoic acid KH. So we get that substrate effect is equal to minus delta Gx plus delta Gh, which is equal to log K X by K H by K, and this is known as sigma X. Okay, and now this equation we know that this is a substrate constant, and substance in the electron and the withdrawing groups it is a positive sign, while in the case of electron releasing groups it is a negative sign. And if we plot this one in this way plot, and we get it sorry, here it is log X by K. I'm sorry. And if we plot, we get a straight line. And this straight line have a slope that is a positive slope and this slope is known as the reaction constants. That is reaction constant, that is delta. It is the slope. And in the case of delta, the electron withdrawing groups it is a positive and it stabilizes, while electron releasing groups it destabilizes and it is negative. If we take the case of this NO2 and hydrogen it is at 0, 0, and if we take NO2 we see that the NO2 has a higher value than that of hydrogen, so Kx greater than Kh. While in the case of OMe and hydrogen, we see that hydrogen is greater than Kx. So it is negative and this destabilizes. Now we can derive the equations for this reaction derivation. That is, if we take the equation y is equal to mx plus c. From the slope from this plot we get that log Kx for substituted rho log Kx plus c for the substituted one. For unsubstituted, log kh is equal to rho log kh plus c. Now subtract both, we get log kx by kh is equal to rho log k. This is log kx minus log kh becomes log kx by kh by a minus b is equal to log a minus b is log a by b. So it becomes log k x by kh log kx by kh, and this is known as okay, and this equation, it is known as the Hammett equation. Now this we multiply each by minus 2.303 RT, then we get kx plus 2.303 RT log kh, which is equal to 2.303 RT log kx plus 2.303 RT log kh. Now we can write it as this is delta gx minus delta gh, which is equal to delta gx minus delta gh. Now it can be written as so free energy, it is proportional to that of the benzoic acids. Here this is a linear free energy relationship between these two. In this cases, Hammett used the benzoic acid deprotonation and for the standard reactions with the substrate parameter sigma, that is okay. So here there is a linear free energy relationship exhibit between the activated substance, activated energy substance, and the parameters of the electron withdrawal and electron donating groups of the substrates. Now in by uses Hammett's plot, we can find various things. First one, we can find the K values, that is rate constant and equilibrium constant can be found out. If there is no any information about it also we can find. Then second one, we can find about the information about transition state of, and third one, by using Hammett's value we can get reaction mechanisms, and fourth, if three values are known, then the fourth value can be calculated by using this equation. So that's all. Thank you.